All right, guys, next up, we're going to take a look at a logistic growth model this time. Again, previous problems have been the exponential growth models. This time, we're going to take a look at the logistic growth. So remember the difference. Logistic growth, that was where we had something that was not growing at all. It was remaining stagnant. Then something occurred, skyrockets in terms of a growth rate, but then levels off again. So again, that's we talked about in great detail yesterday. If you wanted to see or follow along throughout the textbook, or with our textbook, I should say, what we're about to do here is example number 5. That's on page 243. So, again, I don't recall what year our textbooks were written, 2016 maybe, 15, 16, somewhere around in there. But this problem is going to feel weirdly, I don't know, familiar, I think, to a lot of us. So, it goes something like this. On a college campus of 5,000 students, one student returns from vacation with a contagious and long-lasting flu virus. The spread of the virus is modeled by y equals 5,000. I told you, 5,000 over 1 plus 4,999 e to the negative 0.8 t, where y is the total number of students affected after t days. The college will cancel classes when 40% or more of the students are infected. All right, yeah, this problem I feel like could have absolutely been written in a similar fashion in the year 2020, but again, this is an older problem for sure. Like I said, we have all had the the joy of living this type of problem again, to where it actually became more relevant than we'd ever hoped that it would. So again, we've seen how this works, but we've got these logistic growth models. Remember, when it comes to a logistic growth model, you're always going to be, in this class, you'll always be given the model. You're going to be given that y equals 5,000 over 1 plus 4,999 e to the, in this case, negative 0.8 t power. Okay, so first question that we have is how many students are infected after 5 days? So if I were just to recopy my model down, we've got y equals 5,000 over 1 plus 4999 e to the negative 0.8 t. And if we're trying to figure out after 5 days how many students are infected, is this how would we categorize this? Is this a straightforward problem, or is this a really tricky, difficult problem? I'd say pretty straightforward. If we're trying to figure out after 5 days, aren't we just going to let t equal 5? So that means that right here, in place of t, we're going to substitute a 5. And then we calculate. Again, from here it's calculator work. I don't want to undersell the importance. I don't want to make this seem like, oh, it's a piece of cake. You don't even have to think twice about it. No, you have to be very careful how you do the calculations. Don't get me wrong. But we make one substitution, and then now we're going to go ahead and figure out why. So hopefully you're all with me. Again, if you need a calculator, hopefully you've already come up and grabbed one. If you need one, though, come on up. They're right here. But what are we obtaining here in this first problem? When we put 5 in place for t, what do we get? Approximately what? Approximately 54 days. Or no, I need to read my own stuff here. After 5 days, approximately 54 students. I'm thinking of the next aspect here. Okay? Approximately 54 students are infected after 5 days. Does everybody see how we got there? Hopefully we're understanding that in many aspects we can make the argument that we're just letting our model do the work, right? Again, we were given the model. We just had to put 5 in place for t and calculate. Okay? So far, so good, though? All right, go ahead and take a look at the next one. This is where, again, we're going to take that next step. It says, after how many days will the college cancel classes? So remember in the reading, it said that the college is going to cancel classes when 40% or more of the students are infected. So, what does that mean for us? Let me copy the model down here yet again. We've got y equals 5,000 over 1 plus 4,999 times e to the negative 0.8 t. This is the model. So, we know that y represents the population, or how many people are infected. So, again, we're talking 40%. Does that mean that I should just come over here and put a 40? Oh, it's a percentage. So, is that how that works? Also, no. We have to, on the side or background, I tricked a couple people there, didn't I? Okay, we have to figure out what is 40%. What's our target? What's the number? So our target, again, of 40% What is that? Well, what's the total student population? 5,000. And we need to figure out 40% of 5,000. So this is where the 0.4 is going to come in. We're going to have to multiply that by 5,000 to realize that 2,000, that's our target. Does that make sense to everybody? 40% of 5,000, that's the target that we have in mind. So 2,000 is equal to that gigantic mess over on the right side. All right, now, here's the deal. We could do this the hard way, we could do this the easy way. I'm going to assume that we want to do this the easy way, but before we do it the easy way, no, we're not going to work through the hard way, but do you agree that we could solve this in the traditional algebraic sense? Multiply both sides times the denominator, we'd have to distribute everything through, clean things up, move things around, yada, 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 yada. Again, but it could be done. You've done this multiple times just with not as gross looking exponential functions, okay? On an unrelated note, would we agree that 1/2 is equal to 3/6? Equal to each other, right? Okay? So 1/2 is called a ratio, 3/6 also a ratio, and two ratios are equal to each other. We call that whole thing a proportion. Okay? So we have some rules dealing with proportions that oftentimes get overlooked. If we have these proportions, these pieces, the 1 and the 6, these are what we call the extremes. The 2 and 3 are what we call the means. If you wrote it out this way, the means are the middle numbers, the extremes are the outside numbers. Okay, so again, means and the extremes. We've got a property that says that you can interchange means or extremes. What that means is you can literally rewrite this where you flip-flop. So I could put 6 here over 2 is equal to 3 over 1 there. And that's still true, isn't it? 6 over 2 is still 3 over 1. Could we have gone the other way? Meaning with the means. Could we have flip-flopped the 3 and the 2? Could we have written this as 1 over 3 is equal to 2 over 6? Would that have stayed true? Absolutely. Why are we talking about this? What does this have to do with flu virus, and we're dealing with 40% population and yada yada, all this other stuff? So the point that we're trying to make is that 2,000 is just over 1. Wouldn't it be a lot simpler just to switch these and rewrite this as 1 plus 4,999 e to the negative 0.8t is equal to, now we have 5,000 over 2,000. Mathematically, is that going to be a heck of a lot simpler than multiplying both sides by the denominator and all that stuff? Okay, so guys, did everybody see that move? Because I can assure you that throughout the remainder of chapter 3, we're going to use that very move quite a few more times. Okay? All right, so from here, starting to pick things up on the right side, what are we going to say 5,000 over 2,000 is, please? What was that? 5 halves, or we can go decimal, 2.5. Yeah, not to say that we were doing anything wrong if we left fraction. Okay, so it looks more complicated possibly, but would we agree that this just looks like an equation that we could solve back in section 3.4? Okay, so we're trying to isolate the exponential. Subtract the 1 over. So on my left side, 4,999 e to the negative 0.8t is equal to 2.5 minus 1 is 1.5. Okay, getting closer. We still do not have our exponential isolated. Like I said, we are getting closer though. We have to eliminate that coefficient of 4,999. And we've done it on the left. So what we have remaining, e to the negative 0.8t is equal to, now I know that 1.5 over 4,999 is going to give us a nasty decimal. So for that reason, I'm just going to leave it as 1.5 over 4,999. What's my next move? How do I get rid of this e on the left? We're going to apply the natural log. The catch is, if you do it on the left, you have to do it on the right. So on the left side, we have a cancellation. So negative 0.8t is equal to the natural log of, again, we've decided to leave that. Could you have gone decimal? Of course, but again, every time we round within the problem, we just get a little further away from the final answer. Speaking of final answer, we're almost there. We just have to divide by that coefficient of negative 0.8, and we're there. What are we going to say? T is natural log 1.5 over 4,999. Divide by negative 0.8. Sorry? 7.1? 10.1. That sounds way better. Okay, so approximately 10.1. Now, we're talking days. So would we say after approximately 10 days? Approximately 10 days, we're going to be canceling these classes. Okay? So not at the beginning of the 10th day, but somewhere during the 10th day, they're going to, the dean or whoever is going to realize, oh gosh, we hit the 40% threshold. All right, canceling classes. We're gonna send out that email. We're gonna sound the alarm or whatever it is that they would do in that case. Yeah, something like that. Yeah, something like that. All right, Dea, question. So, like, where did the 40% come from? Is that what you're asking? All right, so the key here is where it said that the college will cancel classes when 40% of the students are infected. So here in part B, after how many days will the college cancel classes? Well, they're going to cancel classes once we hit 40%. So what we had to do then was we had to figure out, well, what is the target? What is 40%? So if the total student population was 5,000, 40% of 5,000 is 2,000. So now we knew what we were going to plug in place for our student population. That was our target. Once we hit 2,000, which represents 40% of the student population, once we hit 2,000 students, that's when classes were going to be canceled. Kind of make sense? All right, guys, let's take a look at this next problem. Now, I think I'm going to ask that you make a change here because this bothers me. This was a bad model or that was a bad number or something, but we're going to have to change. So P of T is equal to 1,200 over 1 plus, we're not going to go with 8, we're going to go with 11. E to the, everything else stays, negative 0.01588 T. And I'm going to try to explain why we're going to make that move here as we read through this problem. Okay? But again, please make that change, make that elimination of the 8, and let's go ahead and bring in the 11. Okay? Because otherwise, like I said, technically this model is untrue if we leave that as an 8, not as an 11. Okay? All right, so this problem reads a little something like this. The State Game Commission released 100 animals into a game preserve. The agency believes that the carrying capacity of the preserve is 1,200 animals and that the growth of the herd can be modeled by, new one that we just wrote, where T is measured in months. How long will it take the herd to reach 1/2 of the preserve's carrying capacity? Okay, so here's the deal. If we're starting with 100 animals, max capacity is 1,200. We're trying to figure out how long it's going to take for us to get halfway there. What's half of 1,200? 600. Would you agree that then it makes a big difference as to how many we started with? If we started with 100, or if we started with 500, or if we started with 599, that's going to take different amounts of time for us to reach that mark of 600. Do you agree? Okay. So what that means for us, the way that we can always check this, is that if it says that we're starting with 100, that represents that when T is 0, like before that, like when the time boom initially starts, we better have 100 in the capacity. Okay. Back with that old model, if I put a 0 in place for T, 0 times anything still 0. E to the 0 is just going to be 1. That would leave my denominator as 1 plus 8, which is 9. 1,200 divided by 9 was not 100. Does that make sense? It was like 133.3 or something like that. It wasn't lining up. So now by changing that from 8 to 11, that's going to actually make this true. That if I put a 0 in place for T, 1,200 divided by 12 does match to the capacity. So I'm not sure where the disconnect occurred. I'm sure that it was probably a typo years ago. But again, thanks for making that change, and that's the reason why. Let me stop this video, and we'll actually solve this guy.